Howdy guys, today we will be talking about graphs. What are they? And basic terminologies. Okay, so let's begin. Okay, graphs. So in essence, graphs is basically, I like to imagine it visually, where it has like a lot of different nodes, and these nodes are like connected. So think of a linked list. A linked list was just basically a one-directional graph. A tree was also a graph, but with more rules where like one node could only like point to like down, the parent could only point to the children, children couldn't point back up. But with graphs, you don't have such rules. Basically, anyone is free game. That's why if you like look over here, like you couldn't tell me what the parent of 9 is. You couldn't tell me what the parent of 5 is, Like the parent of 9 you could argue is 5 and 3. But it just becomes a lot less clear. So you can see it visually. It's basically like pathways to nodes, and then be connected as much as you want, as little as you want, so on and so forth. They just have to be connected. There's two kinds of graphs. There's undirected and directed graphs. So undirected graphs, basically, there's just one line. I mean, it doesn't really matter what direction you go. You can basically go two ways directions, or it's like directionless. Versus a directed graph, there's like a specific walkway. So imagine this undirected graph being just a two-way lane, like let's say you're driving on a highway, yes? And you can go both back and forth. Versus a directed graph can be like only one-way streets, where once you get to 3 to 9, you can't go back to 3, at least not the conventional manner. You have to go like around and see if you can get back to 3. So like once you follow the arrow, you can't go backwards. Let's see. Okay, here's some terminology. There's vertices and edges. It's pretty self-explanatory, where vertices here are basically the quote-unquote nodes, and the edges are just the pathways. And this is both true for both directed and undirected graphs. Okay, there are endpoints and end vertices. Okay, so an endpoint and end vertices is basically where an edge ends and starts. So you take U and V. These are endpoints of A. X and Z are endpoints of H and I. Z is the endpoint of J, endpoints, should I say. So on and so forth. Edge is incident. So that's just anything that's like being connected to the vertices. So if we take V, there's an edge incidence for every edge that's basically touching it. So we take A, D, B, these are all incidents, and Z, it would be H, I, J, Y, G, and F would be the edges incidents, so on and so forth. Adjacent vertices are like U and V. So it means is there only one edge connected to it, anything that's quote unquote one edge away, that would be an adjacent vertices. So U and X would not be an adjacent vertex, because although you can get through to it through A and then B, there's no direct path towards it. On the other hand, V and X are adjacent because it only takes B to go across and get to it. Let's see, degree of a vertex. So X has a degree of 5. It basically is just counting all the edges incident. So 1, 2, 3, 4, 5. V has a degree of 3. 1, 2, 3. Z also has a degree of 3. 1, 2, 3. Parallel edges, for example, are H and I. It's when they have the same endpoints. So we can see this very clearly in H and I. And a self-loop is when the endpoint, it just starts and ends at the same vertice. Okay, let's continue the terminology. So now there's a thing called out degree and in degree. This is all basically for directed graphs. So out degree is basically anything counting the number of edges that are going out from it, that are leaving the vertex. So we take T, for example, and has the out degree of 2 because it has 1, 2. We don't count the one going to Q because it's going into it. For R, that would have an out degree of 0, and that's okay. In degree is basically the opposite. It's when arrows are going into, or edges are going into the node. So in T, you would have an in degree of 1 and an out degree of 2. For C, you have an in degree of 1 and an out degree of 1 as well. A sinc vertex is when the out degree is 0. So I like to just see this visually. So let's take A, for example. This is a sinc vertex because it is not outputting anything. It's basically like a SQL. It's just grabbing all these arrows, all these pathways, and it's not spitting anything out. So anything that gets to A will not be outputted again. It like is stuck in A. A source vertex is the opposite. It has a 0 in degree. So take Q, for example. It's just outputting. There's no way to put information into Q, but it's just outputting in it directions. And a Cyclic graph is a graph with no cycles. And we see this, like, if you have a hard time to remember, it's just cyclic. I don't actually know how to pronounce that. It's kind of embarrassing. Cyclic graph versus a cyclic graph. Oh, okay. We have a cyclic graph, which is basically a graph with no cycles. So take this one. When you start at 1, you can't get back to 1. When you start at 2, you can't get back at 2. When you start at 0, you can't get back to 0. There's no way to get back. Versus this one, you start at 0 and you can get back to 0 easily. So 1, 2, 3. So if there's even one cycle, that's enough to say that it is a cyclic graph. Okay, now strongly connected graph. Okay, how you determine if something is strongly connected? Strongly connected basically means that you can get to and from the node from every single other node. So what we do is we're going to choose a node. So let's choose T. And we're going to follow every out arrow path. So just conventional, and we're going to see if we can hit every single one. So if we have T, we're going to see if we can hit every other node. So we have T, we hit Z, we hit C, we hit A, and then this path is done. We notice we can't get to Q and R, so that's already an indicator that this is not strongly connected. But let's say they were connected. There is a second step where we have to basically follow all the in arrows paths. So we basically flip all the edges directions and follow that the opposite way. So we would start at T, we would go to Q because we're going the opposite arrow, and we're basically done there because you can't go anywhere else. There's nothing going into Q. So this would be our second indicator that's not a strongly connected graph. The fancy way, like algorithmically, that you would say of how you would figure this out is by doing depth first search. And if the depth first search, which you will learn in a different video, if your depth first search hits every vertice, then you're good. And if your depth first search hits every vertices when you flip all the directions of all the arrows, of all the edges, then you're good. So here's an example. So I'm going to take A, and I'm just going to follow all the paths. And I should be able to hit every single edge from A just following the conventional path. So I'm going to go A, then F, then E, then B. Okay, and I went back to F, but we already visited that, so we're done. So we're going to go to A. Let's try to hit D, C, and G now. So A and D and G. We already hit B and we already hit A, so we're done there. Okay, let's go back to A, and we're going to hit C and then G. So what I kind of did was depth first search, but all you really need to understand is every single vertices should be able to be hit from A. So if you just find one path to it, then you're good. That means half of the conditions for connectedness is satisfied. So now we're going to do the exact same thing, but instead we're going to flip the directions of all the arrows. So now we're going to follow the arrows going into A or going into G or going into D. So we're going to start at A and we're going to hit G, and then from G we can hit C. We're back at A, so let's try another path. We're trying to get everything else now. So G, we're hitting D, we can hit F, we can hit B, we can hit E, and we're back at D. So now we've hit every single other vertices from A, both from an outward perspective and from an inward perspective. So this is very good. This means that this is connected. Okay, but let's try this one now. Let's try the second graph. So we're going to start at A, and we're going to go to C, and then G, and then back at A. We don't care about that. We're going to go to B, F, D, E. Okay, so the first condition is already satisfied in that every single of these graphs, they've been hit correctly. But let's try this, the second condition that needs to be satisfied. And it's like we flip all the arrows, and can we still hit every single vertices? So we're going to start at A, then we're going to go G, and then C, and then we're back at A. Okay, that's good. We're missing this whole bottom part though, so let's try to get there. So we're gonna go to A, and then G, and then C. I mean, there's no way for us to get to B or to F starting from like an arrow that's going into a vertex. So because of this, we determine that this is weakly connected, because you can't go backwards. You can't go get into A starting from A following the opposite direction of these arrows. So in the end, we determine that this graph on the left is strongly connected, and this graph on the right is weakly connected. Okay, one last topic I'm gonna go over is basically weighted graphs. We use this a lot in networks. So weighted graphs, what are they? It's just basically saying that you have a weighted thing, like there's some sort of value associated with the path. So you can think of it like, let's imagine they're roads. Roads are naturally weighted because a road that's 15 miles long versus a road that's 3 miles long, and you want to store this information, like take Google Maps. Google Maps wants to have a weighted graph to represent like a map, so it can determine what the fastest way to get to your destination is. It would be ridiculous to be like, oh, let's start at E and let's go, or let's take A. Let's go to A and let's go to D, you know? But we notice that D, HD, it takes 21 miles to get there. Whereas A to C to D, I mean, that only takes, if we add up the 15 and the 3, that only takes 18 miles. So it behooves us to first go from A to C to D in order to get there. Another example, let's say you're going on you're planning a trip on a plane, you know, and you want to determine what's the cheapest way to get there. Well, you would naturally have weighted the graph, because sometimes rather than taking directed flights, it's cheaper to take overlaying flights, even though if it takes you farther away. It's funny how that works. So I think that's it for graphs. Don't hesitate to ask any of the TAs for questions if you have any, but that'll be all for today on graphs.